Okay, so before we get into kind of the last thing we're going to talk about in terms of not only concentrations, but really in terms of that whole first purple booklet, all about solutions. So the last thing for that, I just kind of want to talk to you a bit about what we're going to do in terms that we already kind of understand, right? So I often say a lot of this stuff you're an expert in it, you might just not realize, right? So I've made here some Kool-Aid. Don't worry, I washed out the beaker really well. Okay, I'm allowed to drink out of beakers because I'm a teacher here. You are not. But I washed it out really well, and I made Kool-Aid in it. I just didn't have a glass lying around. So you can tell when I made it, it's a little dark, right? It's cherry Kool-Aid because that's the best flavor. If you don't agree, it's okay. Everybody's wrong sometimes. Um, I have it's really dark, so it's quite strong, right? We would use the word strong in our everyday life. If I taste it, it's like super sweet, too sweet. Okay. Now let's use our science vocabulary here a bit. There's a lot of Kool-Aid dissolved in not that much total solution, right? There's not that much solute. Sorry, there's a lot of solute in not that much total solution. We have a high amount of solute compared to not very much solution. Is that sounding familiar? Remember, we can compare the amount of solute to the amount of solution. Whenever we do, we're doing a concentration, right? That's all a concentration is saying how much solute is there in the total amount of solution. So just for simplicity, let's use this one. Concentration is equal to N over V, which N, yes, it's moles, but it's really just a fancy way of saying amount, right? This is just the amount of the solute. So in this case, the moles of Kool-Aid is high in uh, not that much solution total in the total Kool-Aid drink. Okay, so when I drink it, it's concentrated. Its properties, like we said, as concentration goes up, right, the properties of the solution get very apparent. So what are the properties of Kool-Aid? Well, it's red. So this is very, very red, right? Very red. It's Kool-Aid is sweet. This is way too sweet. Okay, I like my Kool-Aid sweet, but this is too much. Okay. Um, it's a molecular compound, so hey, it shouldn't be conducting electricity anyway. Let's see if it does. No, it doesn't, and it shouldn't, right? Because it's a molecular compound. Uh, I guess I should say it's just sugar, right? Kool-Aid is basically just sugar and food coloring. Okay. Um, so right now it's sweet. Now, what would you do if you had Kool-Aid that was too sweet and you had a whole bunch of water lying around? What could you do? Well, you could add the water to the Kool-Aid, right? Water it down, we might say. Now, what am I really doing? This is the volume of the solute here, right? Not much. If I increase the volume by adding water, notice what's happening to the Kool-Aid. It's getting, first of all, a little fainter. It's getting a little bit fainter. And why did I set up to do this, or why would you maybe set up to do this? Because I want the properties to decrease. So it got a little less red, right? It's a little fainter now compared to before if I hold it up against the white background. And let's see how it tastes. Perfect. Okay, so what did I do there? I made it less concentrated so that its properties were less apparent. The properties of sweetness and the properties of redness. Yes, it's still pretty red, but remember before it was like blood red. Okay, now it's a little fainter. It's a good Kool-Aid color. Okay, so what did I do there? I made the volume of the solution bigger. I didn't add any Kool-Aid, right? I made the volume of the solution bigger. So what I did was I made this number bigger. I made V bigger, right? I'm just going to use an arrow to say I'm making it bigger, okay? Um, I made it go up. So that means when I'm calculating C, now I'm dividing by a bigger number. If you're dividing by a bigger number, you're going to get a smaller answer, right? Take something and divide it by 2, and then divide it by 3, and then divide it by 4, you're going to get smaller and smaller and smaller answers, right? Uh, so as I make V bigger, I make C smaller. So what did I do? I added volume in the form of water to lower the concentration. Now, if you think back, we said that if something was not very concentrated, if there was a low amount of solute, in this case Kool-Aid, to solution, Kool-Aid powder is the solute. The solution is the actual Kool-Aid, the drink, right? Um, if it's low, we would call that a dilute solution. If the concentration is low, we'd say that's a dilute solution. So that process that I just did there, where I'm decreasing the concentration by increasing the volume, making the Kool-Aid less sweet, less red, that is a process known as dilution. I'm making it more dilute, okay? Or I'm making it less concentrated. Now, what if I was out of Kool-Aid? I couldn't go to the store and get more Kool-Aid. Powder. I keep saying Kool-Aid. I mean Kool-Aid powder, okay? If I couldn't go to the store and get more Kool-Aid powder, and now I went too far. It's too watery. It's not sweet enough anymore. Okay, let's pretend. What could I do? I can't pour it out. That's not going to make it any sweeter. Right? That just changes the cup it's in. I can't add water. That's just going to make it worse. It's going to make it less sweet. I'm going to dilute it some more, right? If I can't add more Kool-Aid powder, I need to, once again, if I want to make it sweeter, let's say I went too far and it's not sweet enough, well, what if I tried to do the opposite? What if I, instead of increasing the volume, I was able to somehow decrease the volume so that the concentration, now I'm dividing by a smaller number, so the concentration increases? Would that be something I could do? It turns out it is. Okay, but you got to be a bit tricky here. You got to be a bit, there's a clever way to do it. Okay, so what we have to do is wait. So I'm going to repurpose my sodium one from earlier, okay, from earlier videos. Remember my sodium chloride, my salt water solution, okay? I've got that there. That's my salt water solution. I'm going to let that sit for a few days, okay? I will try to get it in for the end of the video. I don't know if it'll be ready in time, but what's going to happen when I let this sit here, I'll move these away for now. What's going to happen when I let this sit here is that the water part of the solution is eventually going to evaporate, right? If I leave it out long enough, it will evaporate, slowly but surely. The solute, the salt in this case, right, it's a solute dissolved in the solvent, will not evaporate. It actually gets left behind. Okay, and to prove that to you, that's why I got to leave it here for a few days. But to go back to my Kool-Aid now, if the solute, the Kool-Aid powder, is getting left behind when the solvent, the water, evaporates, then the concentration is actually going to increase, because that's going to be happening, right? Now my volume actually will be going down. The water level will be getting lower and lower and lower, but the Kool-Aid will be staying behind, and so the concentration will go up. Remember, N is the amount of Kool-Aid, okay? So I'll leave this here for a few days. Hopefully I can get it in for the video, and you can see just really the whole point is to prove to you that the salt is left behind when the water evaporates. Okay, so I'll try and show you that in a few days. For you, it'll be right away. For me, it'll be a few days. Okay, so yes, let's actually get to what that means. Now that we have a grasp, I just wanted to show you that we know what dilutions are. We deal with them, right? You ever made Kool-Aid that's too sweet? You wanted to water it down a bit? You know what a dilution is. You've done them, okay? Let's actually get into the math of it now a little bit, and then that wraps up our solutions section of chemistry.
Okay, so it's not completely finished, but you can see on here, right? See on the edges, as this has evaporated over the last couple of days, there has been some salt left behind. If we went longer, it'd be even more apparent. Okay, on the stir stick that I left in there, look at that. That's a big, basically, chunk of salt that's come out of the solution. So the solute gets left behind when the solvent evaporates. So the solution volume lowers and the concentration goes up. This is now saltier than it was before.
Okay, so if you're keeping up in the notes, we're on page 13 now. Okay, that's that purple booklet. Again, those notes are on Google Classroom if you did not bring one home before last week. There's also other options. You can just take notes on scrap paper, whatever does you best, okay? So many, as we talked about there, right, why do we care about dilutions and concentrations? Often this stuff is sold in a very concentrated form. The chemicals, for example, that we get into our school that go to Mrs. Tyrath's room, they're very concentrated so that we can dilute them to whatever concentration we want, right? That way it saves money on packing, on space, on costs, on materials, right? You can fit a whole bunch of very concentrated chemicals into a truck. You can't fit a whole bunch of dilute chemicals into a truck if you want the same amount. Think about laundry detergent at home, right? Your parents or you might buy um, very concentrated laundry detergent. That actually saves money. It saves plastic, which is good for the environment, right? By making it very concentrated, because then you can dilute it to whatever concentration you want. So, like we saw with the Kool-Aid, to dilute a solution, we add solvent to increase the volume, and therefore decrease the concentration, right? Increase the volume without adding any more solute will decrease the concentration. So that's what I was showing you before with the C goes up, sorry, V goes up, C goes down. That's the main way that we do it, honestly. It's usually dilutions. However, like I said, you can also evaporate solvent out, which decreases the volume and increases its concentration, right? So that's just the kind of opposite way around. Okay, so here's our formula for it. Again, this is on page 10, okay, of your data booklet, but we have that CIVI equals CFVF. Okay, now let's break this equation down a bit because it's interesting. Why is this true? Remember, in all of our dilutions, we never added any Kool-Aid, right? We never removed any Kool-Aid. We might have added water, the solvent, or removed the solvent, but we never changed the amount of Kool-Aid, the solute, okay? So N in C equals, oh, don't want that, in C equals N over V, N, remember, represents the solute, or the Kool-Aid, if we're using our example, right? So in C equals N over V, this is the solute. So let's just manipulate this really quick. C was N over V. If I multiply both sides by V, then hang on, what have I got here? N equals C times V. So CV, what is this? This is N. And you notice initial, initial, final, final. So why are we allowed to say that the concentration initial times the volume initial is equal to the final concentration times the final volume? We're allowed to say that because we didn't add any Kool-Aid. We didn't remove any Kool-Aid. So the amount of Kool-Aid, the number of moles of Kool-Aid, is equal to the number of moles of Kool-Aid in the end. Because we didn't add any, we didn't remove any. So this is why this equation works. Okay, do you super need to understand that to use the equation? No, if I'm being honest, but it never hurts to understand things in a few ways, right? So there's our equation, and it works because CV is N, right? It works because C times V is N, and it works because C times V is N. So CI does not equal CF, VI does not equal VF, but when you multiply them together, you get N, and those are equal. NI is equal to NF. Okay. One special note for all of these types of questions, I'm just going to say it up top so you know, okay? You need to be careful, very careful, about what the question is asking you. So be careful about whether the question is asking you for final volume, in which it just says, what is the total final volume, okay? Versus when it's asking you V volume added. Those are two different questions, okay, or two different ways of asking the question, right? So what I mean by that is, for example, if I say I started with, I'm just going to make up numbers, but if I say I started with 90 milliliters and I ended up with 100 milliliters, okay, my final volume is 100 milliliters because that's what I ended up with, right? But the V I added would be the difference, would be 10 milliliters, right? To go from 90 to 10, well, 100 minus 90, sorry, to go from 90 to 100, 100 minus 90, where I ended up, minus where I started, final minus initial, right, would be 10. 100 minus 90 is 10. So kind of the same question, but two very different answers, right? If I go from 90 milliliters to 100 milliliters, my final volume is 100 milliliters. But the volume I added was only 10 milliliters, okay? So just be careful, read carefully, okay? Does the question want to know what your final volume is, or does it want to know how much you would need to add or remove? Sometimes it's remove. Okay, let's just jump right into some examples. So the nice thing about this equation is it's usually one step to manipulate. You have 65 milliliters of a 0.759 mole per liter solution of sodium chloride. So there's a little bit of reading comprehension in these questions, like all questions, right? But we have this. We already have it at the beginning. Okay, then it's saying calculate the final concentration. So milliliters, that's going to be a V, and that's initial, right? Because I'm starting out with that. Truthfully, it doesn't matter which one you call I and which one you call F, as long as you don't mix up I's and F's, right? So what I mean by that is, as long as I call that the same letter as this, right? So as long as I didn't make one VI and one CF, it would actually still work out. If I had made them F's, I would get the right answer in the end. I would just kind of think I was looking for something else. So VI is 65 milliliters, C initial is 0.759 moles per liter. Calculate the final concentration, so CF equals question mark, of the solution if it is diluted to a final volume of 100 milliliters. So VF equals 100. Whoops, I'm just going to write it at that. VF, don't need to worry for now. Okay, so like always, let's do our givens, our required, and choose an equation based on that. So VI equals 65.0 milliliters. CI 0.759 milliliters. Oh, not milliliters. C, so it's moles per liter. Okay. VF is equal to 100 milliliters. Not 1,000, 100. Now I know what you're thinking. You're going, hang on, we're using C's and V's. Shouldn't all of those V's need to turn into liters? And you're absolutely right, usually. Okay, usually 100% you should. And you can still, nothing will go wrong if you do. We just don't need to. And I'll show you why if you don't believe me, okay? So just remind ourselves, I'll get there in a sec, what I was just saying, but CF equals question mark. Okay, so as always, we need an equation that has all four of those and nothing else. So if you go to page 10 in your notebooklet, you'll see that our friend is CIVI equals CFVF. Okay, so CI times VI equals CF times VF. Okay, now as always, what do we want? We want CF. And like I said before, this is a nice equation to manipulate because it's almost always just one step. If I want CF alone, I want it by itself. What's happening to it? Well, the only thing that's happening to it is being multiplied by VF. Okay, so what's the opposite of being multiplied by VF? It's being divided by VF. Okay, to undo that multiplication, we need to divide. Now I divide this side by VF as well. See what I mean? Not too bad to manipulate because look, we're already done. So I'm just flipping the sides here. I'm just taking this side over to this side. CF equals CIVI over VF. Aha. Okay, and lo and behold, we're done. CF is by itself. Okay, just gonna move up here to give myself some room while I keep plugging in, but all I gotta do is plug in. So here's where I'll show you what I mean about how it actually, again, here doesn't matter what units we have as long as we're all on the same page. As long as we all use we use the same units for every quantity, okay? So CF equals CIVI over VF, so that CI is 0.759 moles per liter. Okay, VI is 65 milliliters. Getting a little squished for room. Divided by VF is 100 milliliters. And here's where you'll see what I mean. Okay, always write in your units so you can check your work. Because look, yes, I didn't turn them to liters, which you normally should when you see C's and V's. You should make the V's into liters. But look, I have milliliters over milliliters, so it doesn't matter. The reason that works is that the ratio of 65 milliliters to 100 milliliters is the same as the ratio of 0.065 liters to 0.1 liters. Okay, but that's neither here nor there. See how they cancel out like that. And what are we left with? Always check your work. We got moles per liter. And what are we looking for? A concentration. Good. So we should be getting moles per liter, right? That is good news. We're feeling good about this question. So the final concentration, if we change the volume from 65 milliliters and we add water until it's 100 milliliters, the volume is, it's going to be 0.493 moles per liter. That'll be the new concentration. Okay, always check, think, ask yourself, does this make sense? We added water, so would this water get saltier or less salty, right? If we were to take a sip, would it now be less salty? Well, we watered it down, so the concentration should be lower, right? And good, it did. It went from 0.759 to 0.493. Never be a robot, always think about your answers, right? That does make sense though, that checks out with what I would have predicted. Look at the next one. Calculate the final concentration. So we're looking for, calculate the final concentration. Okay, there we go. So that's CF is what I want. Of a solution prepared by adding, okay, so be careful here, by adding 100 mils of water to the original solution. Use the following information to answer the next 4 questions. Okay, so we're still talking about this old stuff, okay? It's just saying we're doing something different now, okay? So forget this stuff, forget question 1, question 2, but still using that information. So we have 65 milliliters, nothing's changed there, VI is still 65 milliliters. Oops, that is not an L. 65 milliliters. CI, nothing new. 0.759 milliliter. Nope, moles per liter. It's a concentration. Getting tired. Okay. CF is what we want to know. Okay. And here's the thing. What is VF? Is it 100 milliliters? No is the answer, right? It is not 100 milliliters. That is not going to be the final volume because we're adding 100 milliliters. And there were already 65 milliliters there. Okay, so we're going to take those original 65 milliliters, we're going to add 100 to it. So let's just do that, 65 mil, and then we're going to add 100 milliliters. That means in the end, we're going to have 165 milliliters. So that is VF, not 100. Be careful, okay? It's tricky, but it makes sense once you notice it. Okay, so go to your data booklet, find the equation that has all that stuff, but it is our new friend CIVI equals CFDF. Okay, now once again, we want CF. We need it by itself. It's being multiplied by VF. This is just like last question, okay? So we'll divide, do the opposite of multiplying. The opposite of multiplying, you must do it to both sides, right? And so CIVI over VF equals CF. Just gonna bring it up here to give myself some room to work, and also gonna switch the left and right side because that's usually how we're used to writing it. So CF equals CI times VI, CI 0.759 moles per liter. Oh boy, I'm in another room. Times, oh geez, VI 65 mils. I may not have room for units. Oh, maybe. There we go. Just squeezed it in there. Okay. CF, not the best, but it'll work, over my VF, right? So CIVI over VF, and VF is 165 milliliters. Cool. So plug that all in, be careful with your calculations, make sure your units do cancel the way you want them to, and good enough they do, milliliters over milliliters, leaving me with moles per liter. Perfect, that's what I want. The final concentration then is 0.299 moles per liter. Okay, check that I answered it the way I wanted them to. I did, right? 3 sig digs, not because of this. This would suggest 4 sig digs, but don't forget, right? We're still using these numbers, so they limit us as well. So it's still going to be 3 sig digs. Okay, let's do the next one. How much water do you need to add to the original solution to obtain a solution with a concentration of 0.2 moles per liter? Okay, so they're using the add thing again, so be careful. But nothing has changed in my initial, right? We're still using that same one that's up in the box at the top of the page. VI equals 65 milliliters. Just gonna cut it off. It's kind of bleeding into this one. CI equals 0.759 moles per liter. But now it's saying, how much water do I need to add to obtain a solution with a concentration of 0.2 moles per liter? So I want to end up with that as my concentration in the end, my final concentration. Okay, now this is a calculation, well, I for one do all the time, right? When I'm making up lab chemicals for labs, I have to do this to figure out exactly how much to make. or how much to put in to get the desired final concentration that I want. How much distilled water do I add to an acid, for example? But this is also quite common just in all kinds of industries, right? And even in your home, right? Like when you're cooking, you kind of know, for example, how much water you need to add to get to the right taste in the end, right? So this is something you kind of, a calculation you might have done even though you maybe didn't realize you were doing it. And so it's saying, yes, VF is not the final answer, right? VF, because we are looking for how much water we need to add. So VF will not give us the final answer. VF is not the final answer, I should say. But we do need to figure out how much we end up with, and then subtract that from what we started with to figure out how much we added. Okay, so first we're going to find what we added, sorry, what we ended up with, so that we can backtrack and figure out how much we added. So like always, check formula sheet for the one that works. And in this case, once again, it's this guy. And I'm just going to actually, sorry, I'm going to put a little note that it won't be our final answer. That's what that little star means. Okay, it's not our final answer, but it is important to know. So CIVI equals CFVF. We want to get rid of CF. Good. Okay, we want to get rid of CF so that we can know VF. So then VF is equal to CIVI over the final concentration, like we said there. And again, I'm just canceling out what canceled and then flipping the left side with the right side because that's how we usually write it. So CI is again 0.759 moles per liter. VI is 65 milliliters. And CF is 0.2 moles per liter. In this case, it's not the milliliters that are going to cancel like before, it's actually the moles per liter. That's a unit, so that cancels. Moles per liter cancels with moles per liter. Okay, and so we're going to do 0.759 times 65 divided by 0.2, and we're going to get that VF is equal to, I'm getting 246.68. 246.68. Be careful, what are our units? Well, milliliters, that's all we're left with, right? So we have units of milliliters. I'm keeping some extra decimal places because I know I'm going to have to use this answer again here in a sec. Okay, I'm just going to switch back to black to kind of show, so let's maybe call that, do we want to call that step one? So one, find VF. It's not quite a two-step question. I guess it is a two-step question, but now we're going to go into, I guess, step two, find, I'm just going to call it the change in V, but it's V added, right? That's the V that we added. Whatever our change was how much we added. Now, how do you get any change? You take your final minus your initial, right? Where'd you end up minus where you started. Okay, if you look at how many years, how many years have gone by since you were 11, let's say, right? You're now in grade 11, so most of you are 16, right? So we would say 16 minus 11 is 5, so 5 years have gone by since you're 11. Same thing here, right? Oh, sorry. So here we'll do, to find how much volume we added, we will say what we end up with. So the volume we added is equal to VF minus VI. Okay, the final volume minus the initial volume. And so we know VF now is 246.68 milliliters minus, we started with 65 milliliters. And so the volume we added, I'm getting 181.68 milliliters, which now to my 3 sig digs would just be 182 milliliters. That's what we needed to add. So to go from 65 to 246, or 247 once you round, we needed to add 182. That's what it's saying. Okay? So common mistake would be to put a box around this and call it your answer. Okay? That's a very common mistake I see. So don't fall for it, right? When it says add, maybe make a little note for yourself, add somewhere, just to remind yourself that you're not going to just find VF and be done. You're going to have to figure out what you added to VI to get VF. one extra little step, okay? All right, last one. How much water needs to evaporate from the original solution, evaporate question, from the original solution to leave us with a solution that has a concentration of 0.890 moles per liter. So again, nothing really new here for the initial. The volume initial is still going to be 65 milliliters. The initial concentration, like always, has been 0.759 moles per liter. We're just going back to the same initial conditions every time, right? Has a concentration of, we want to know, it will leave us with a solution after this evaporation. It'll leave us with a solution that has a concentration of that. So CF is 0.890 moles per liter, right? That's the concentration we're going to end up with after this evaporation. So again, we do want to know VF, but is it the purpose or the point? Not really. We want to know what the difference is between VF and VI, right? That's what we really want to know. So I need an equation that has VI, CI, CF, VF, and here's our, sorry, just going to give myself some more room over here. CI, VI equals CF, VF. Okay, so like I said, these are usually pretty nice to manipulate because it's always one step. So I want VF, it's being multiplied by CF. So if I want to get rid of CF, I got to do the opposite and divide both sides by CF. Now it's gone from that side, and we've got VF equals CI VI over CF. And VF is equal to, what's CI? It's 0.759 moles per liter. The VI is 65 milliliters. And we're dividing by the final concentration that we're going to end up with if we let this evaporation happen, and that's 0.890 moles per liter. Okay, plug that all in your calculator, and then we get not our final answer, right? But we do get 55.43 26. That's a lot of, I'm just leaving some extra sig digs because I know I'm going to have to use this number again. How did I know that was milliliters? Let's check. Moles per liter canceled out with moles per liter, and that left me with milliliters. Okay, good. So that's my final volume. Now, this question is, right, if this question had just said, what's the final volume? Good, you're done. But be careful, this question didn't say that. It said how much water needs to evaporate. So what did we start at? We started at 65 milliliters. So how much water needed to leave for us to go to 55 milliliters? Well, again, same idea, okay? Change in volume, how much change is where did we end up minus where we started. So the change in volume here is going to be 55, the final volume, 55.4326 milliliters minus our 65 milliliters that we started with. And you're probably noticing, hey, we're going to get a negative number. We sure are. That's okay. Okay, I got negative 5.57 milliliters. What does that mean? The change being negative? Well, think about like your bank account, right? If the change in your bank account is negative, that means you spent money. Same thing here. The change is negative, so some volume was lost. The volume is ended up lower than it started. So there's nothing wrong with that. Okay. Oh, wow. Look at this. There's a mistake in the answers. Okay, good thing I caught that. Look at that. Answer 55.4 mil. It looks like I fell for my own trick. Okay, so don't be me, right? Don't be me here. VF equals 55.4 and I went and put a box around it. That's not the answer, right? No. This is the answer. Okay. All right, so that is the last of the solutions type booklet for notes anyway. Here is some whiteboard practice that I normally would have given you, so you can try this on some scrap paper, wherever you want to do it. There's all the answers here, okay? And you can now do the entire extra practice mixed concentration examples. That's on the Google Classroom post with this video. As well, once you are feeling comfortable enough with it, so I wouldn't just jump right into it, I would do some of the practice, okay? Make sure, try a few whiteboards, try the mixed concentration examples, but the Google form assignment for this week, you now have done all of that. Okay, so you'll be able to do that. Don't forget that will include Lewis diagrams as well, and yeah, just some of the basic stuff that we started the week, well, last week. Okay.